All right, welcome everybody to another Rust stream. Today is going to be a little bit different than we've done in past weeks. Today we're going to be talking about a data structure and specifically talking about linked lists. The reason that I wanted to do this is because still, after many, many years, when people are coming, especially from C and C++ background, they often ask, or they often attempt to do a linked list as their kind of first thing that they do with Rust. And it's a horrible idea. Linked lists in Rust are not necessarily difficult, but certainly more difficult than they are in C. And it's, I wouldn't say a very beginner-friendly exercise. It's more of kind of an intermediate or like late beginner exercise. And so people often get frustrated with that, not realizing that, hey, Rust isn't C and C++, it's a different language. And so things that are easy in one language might be hard in another and vice versa. And so what we are going to be working on is looking at linked lists, and specifically a singly linked list today, because doubly linked lists are actually, I wouldn't say hard, but are really like you require kind of intermediate or high intermediate understanding of Rust to get right. We're going to be looking at singly linked lists today because it does give you a good impression of how Rust works, and we will touch on a lot of interesting topics in the language. All right, so without further ado, let's go over to the screen real quick. So what we're going to be looking at today, kind of I think the real kind of gold standard when it comes to understanding linked lists is the Learned Rust with Entirely Too Many Linked Lists mini book that I believe was originally written by Gankra back in the day, but I think is now kind of maintained by the Rust project itself. And I'm glad that you're watching this, but if you prefer reading things, then this is a really great resource, and I definitely recommend you take a look here at this. Real quick, my chat has been lost. All right, there we go. So this is a really great resource to take a look at. And you can follow along using this. And of course, today we're only going to be talking about singly linked lists because I only want to do about an hour of streaming today, and I don't think we'll have time to get beyond that. But if people like this, then let me know, and we can continue using this resource as a guide to learning about Rust through linked lists. The thing to say about linked lists as well is not only are they like not super trivial to implement in Rust, but they're also generally a bad idea. And one great thing about this resource here is that it goes into an obligatory public service announcement about why linked lists are generally a bad idea. And so you can read about here, why you should use a linked list, and it's usually oftentimes for very esoteric reasons. And so in Rust, when you're asking yourself if you want to use what kind of collection you want to use, you basically should not reach for a linked list unless you are absolutely sure that that's what you need. And maybe you actually do need a linked list, but you should know a reason why. You shouldn't just grab for it because that's kind of the standard. There is a linked list in the Rust standard library, so if you need a doubly linked list, for instance, the standard collections linked list is probably one that you want to reach for before you kind of start writing your own. But I'll be perfectly honest with you, I've literally never used this. I've used basically every other collection in the standard library multiple times for many different projects, and I've never used the linked list collection. I'm sure there are plenty of people out there that use standard collections linked lists all the time, but I'm just saying I've been writing Rust for quite a while now, and I never use this. The go-to collection in Rust if you're just starting out, if you need kind of just a normal collection, is VecDeque, and so most of the Rust code you'll see will kind of default to VecDeque unless there is some other reason to use it. And of course, if you need a hash map, there's hash map. But then there's kind of other, I would say, other collections that are specialized versions of vec and hash map, and hash set, I guess. Although hash set, you can just use a hash map for that as well. All right, so enough talking about the standard collections and stuff like that. We're going to start writing a linked list. And chat, let me know if you have any questions, because I hope to make this a little bit interactive so that we can kind of get ahead of ourselves and hopefully go down some like not right paths so that we end up making common mistakes and talk a little bit about why those are mistakes. All right, so I'm going to go over here and just do cargo new linked list as a project, and it's going to be a lib project, and we'll just open up linked list here in VS Code, and wow, that's big, and get started here. Let me know, hopefully everybody can see this fairly well. I'm just going to make it a tiny bit bigger here. We can make this smaller for now. All right. And 1 second here. Cool. So looks like it's visible for everybody. So the first thing that normally what you would do when you have a linked list of some sort is think about, okay, that linked list can either be, let's go ahead and get rid of the, we'll leave that for a second. We'll leave the test for a second. So we'll just think about our linked list like this as being either it's an empty list, or it's a non-empty list. We can do non-empty here, and it's pointing to some other thing, right? And so really we could think of this as like a node in our list, and the node is either empty, it doesn't have anything inside of it, or it's non-empty and it has something inside of it, the value that we're keeping in our list. Like let's just say for now it's a U32 of some sort, and then maybe it's pointing off to it has another, it's pointing to another node, and so you might be tempted to write something like this, and this is the first problem that people often run into when writing linked lists in Rust, where we have a recursive type here. So node is either empty or it's non-empty, and if it's not empty, then it kind of contains a node. And of course, that means that you can like recursively have as many non-empty nodes in this thing as you want. And everything in Rust is stack allocated. So when we create a node, like down here in our test, let's go ahead and create a node here. We wanna like, Rust will kind of look and see, okay, how much space does this thing take up on the stack? And then I can, I will generate code that takes up that much room on the stack. And so, if I write node is not empty, okay, and node is not empty, node is not empty, and it has, 1 in here, let's say, and then node is not empty. And it's just going to keep on going for forever and ever and ever. And it might end up being, infinitely large, or it potentially can be infinitely large. We don't know how big a node actually is. Of course, when we're creating a node here, we'll know how big it is. But if we have a function that takes, my func here, that takes a node, sorry, not none, a node here, how much room in memory, how much room on the stack does this node take? We don't actually know, because it can be, it can be 5 nodes deep, it could be 1 million nodes deep. We don't know, and Rust doesn't play well with that. Rust has to know for stack allocated things how much room it's actually taking up. Okay. And so the first thing, and I think if you go ahead and actually run this, it will give you this has been written so many times that they've actually built in a compiler error message here that gives away what's happening here. And it says, node is a recursive type and it has an infinite size. We don't know how big it is. It can be infinitely big. And it's recursive without indirection. Meaning that it's okay to have a recursive data structure where it's infinitely big or as big as memory can hold or whatever, but we can't do that on the stack itself. We have to kind of do it indirectly by having this thing live, having a pointer to somewhere else, so that the node itself is always a certain size. It's telling us here to insert some indirection here through a box or an RC or an just a plain reference or something like that to make node representable, to ensure that node has a finite and well-known size, that node is always the same size in memory. So we can go ahead and do that here by wrapping it in box here. And so now, we have an actual linked list here in a way, right? We have a node. It can be empty, and or it can be non-empty. And if it's non-empty, then it has, an element, and we're kind of hard coding it to U32 here. And along with that, it has a pointer to the next thing in line. And that next thing in line can be empty, can be the end of the list here, or it can be non-empty. And it will contain a U32 and the next thing in line. And so this really is kind of the minimal the minimal thing that we need in order to implement a linked list here. And so, it's not the most usable, right, in the world. So we probably want to build some abstraction around this. And there are other problems with it as well that we'll talk about in just a minute. But this is kind of the minimal that we need in order to build up our linked list. And if you're confused about the infinite size thing, chat, of course, you can let me know right here. But if you're watching this later on and you're confused about it, just remember that Rust always needs to know if you have a value of a given type, that value should always be the same size in memory. And the only way that we can get that to work is by inserting this indirection here, because a box node is always going to be the same size. It's going to be a pointer, because that's what a box is. It's a heap allocated owned pointer here. So we know how big this variant is here. It's a U32, which is 4 bytes big. And it's a pointer, which on my machine is, I'm a 64-bit machine here. This is 8 bytes big then. So we know that this, at least on my machine, on my architecture, is going to be 12 bytes big. All right, cool. Let me know if there's any questions here. If we look back at learning Rust through too many linked lists here, you can see that this is discussed here, the actual layout that we have, they end up doing basically exactly what we end up doing. They have a list here. It's either empty or it's an element. They're using different names. They're using I32 as the hard-coded type that it has, and then they're boxing the list here. But as they point out here, this is a really foolish definition of a list. For two reasons. We're allocating a node that just says, hey, I'm not actually a node. And what they mean by that is, like, let's create a one element list here. So our list is going to be a node, and it's going to be non-empty, and it's going to have some number in it, 1091. And then it needs to have another node in it. So we have to box up that node, box new, and then node. And if we want the list to end here, we say empty, like this. And of course, we need to bring in these types into our tests so that we can actually use them. So this is a little bit wasteful in that this right here is basically just saying that the next element in the list is empty, but we're calling into the into the system allocator here. We're actually allocating memory on the heap here, just to say that this element is empty here, which is a bit of a shame, right? It would be much nicer if we didn't have to do that. Chad has a question here. What's the difference between using ampersand and box? Both are pointers, yeah. So the question is, we use box here, which is an owned heap allocated pointer here, which we've chosen to do. When we looked at the error message before, it was saying you can use RC, you can use box, you can use ampersand. Why don't we use ampersand here? So let's give that a try. Let's try to use ampersand and see what we end up with here. Okay. Well, first of all, we're going to get basically a syntax error here, where it's saying we're missing a lifetime specifier. So what it wants to know is you have a reference to a node here, a pointer to a node here, that's going to live for a certain amount of time, and we need to know how long. How long does it live for? And so in Rust, we don't need to know that for box, for instance, because box is an owned pointer, meaning that we decide when we have a box when the value that it's pointing to is destroyed, is cleaned up. But with references, we don't decide that. We're simply borrowing the value. So there's some other variable in our program that owns that node and will decide when to destroy that node. And we're borrowing it, so we need to how long does this thing live for? Because we have to prove to the compiler that it lives for a shorter amount of time than the node itself actually lives, right? So it's asking, okay, give me a lifetime here that I can deal with. I need to understand how long this thing is, and lifetimes are always generic, so we need to come up with a lifetime here, and by convention we usually use tick A as the name here, okay? And then we get another syntax error and saying tick A, I don't know what that is. And that's because tick A is some lifetime we just called A. We're just coming up with a lifetime, and we're giving it the name A. We could call this literally anything except for static, which has special meaning. We could say tick foo here, and that works as well. Or rather, doesn't work for the same exact reason, right? It doesn't know what foo is. We'll stick with a convention here and just do tick A. And the way that we say this is we come up here and say that node is generic on this lifetime A. And the way that you can think about this is the following. The way that you can think about this is that this node, when we have a node, it is constrained to live for as long as some lifetime A. And that is however long the reference that node contains inside of it lives for. Because it doesn't make any sense if we have a node that lives for, a certain amount of our program, and let's look at it visually here. If we have a node that lives for this long in our program, but that node contains a pointer to another node that lives this long, well then for this part of our program, we'll be carrying around a dangling pointer. We'll be pointing to some node that is junk memory, right? And that's not very good. So we're kind of tying this outer node value here to the lifetime of the inner node here. All right, hopefully that makes sense. And of course then node itself now is generic on a lifetime, so we probably want to do this here. And this works fine. You'll notice that we're getting some warnings here or whatever, but this this compiles. This part right here compiles, and in fact, if we remove this, our program is going to compile just fine here. This is totally fine. The part about this that's difficult though is that this is very hard to use, right? Because we need to explain to Rust that node will live for some lifetime A, right? And so how do we do that? Well, we can go ahead and say node is going to be empty like this. And we'll go ahead and borrow it right here. And now we can say, oops. And this works. But if you keep trying to actually use this thing, like, you know, once we start passing this around and stuff like that, it's going to be very difficult to actually use. So we can use tick A here. That's totally fine, but it gives us less control over how we're using our node, because now node is going to be constrained to some lifetime tick A here, whereas before we didn't have that constraint because we were using owned pointers in a box. Let me know if that makes sense to you. And if not, we can kind of take a look at it in a different way. And Chad is kind of joking around and saying, you know, but we can get rid of this generic here by using the one like non-generic lifetime that Rust comes with, which is tick static here. And this is also possible. Oh, of course, doesn't need that. This is also possible, but again, you're going to run into a lot of situations when you try to use your linked list where this will be not so useful. All right, cool. It looks like chat is saying that makes sense, which is good, and it looks like we've got some malloc trolls in our chat as well, wanting me to use malloc. Hey, this is not C, so we're not going to use malloc directly, unfortunately. All right. Cool. So we're going to go back to the box syntax that we had before, like this. All right. So, whoops, sorry about that. Then going in here, you know, we talked about the problems that we had here. We're allocating the last element in there just to say that it's empty, and one of our nodes isn't heap allocated at all. So you know, it says like on the surface, this, you know, this kind of cancels itself out and stuff like that. But you know, this isn't ideal, right? We would rather have a layout that is uniform, where each element has the same layout. And if you want to read in like some possible other ways that we could do this with empty elem then empty, that's also not so nice and stuff like that. But instead, we can kind of separate out the idea of a node from the idea of the list as a whole. And I wish my phone was not turning off so that I could continue to see what chat is up to. Real quick here. All right. All right, and chat is also asking, they're curious about the rules for when a box is freed. So box in Rust is an owned pointer. It owns the value that it points to. So this box owns this empty node here. And in Rust, things are freed, things are dropped is the term in Rust, when they go out of scope. So as soon as this box new goes out of scope here, and this box is in turn owned by this non-empty node here. So when all of this kind of goes out of scope, which happens just in line 12 here, then recursively everything will be freed here. So that's very important in Rust. When you have an owned variable, at the end of the scope of that owned variable, that's when the owned variable gets freed, it gets dropped. So hopefully that helps a little bit. So here, what is being suggested is that we break up the idea of a node with the idea of a list as a whole here, where we say something along the lines of enum list here, right, is going to be empty or a link of some sort, right? And I guess they call it more. We can stick with that as well. more, or I like the name link. And then we're going to box up our node here. And then node is no longer an enum. Node itself is actually going to contain the element and the next list. So element here, element. We were saying a U32. And next, just like that. All right, and this has a more uniform layout then. So the tail of the list never allocates extra junk, which is great. And there are some other things here, that it's a null pointer optimized form, which we're going to talk about in just a second. And all elements are uniformly allocated, which is good. This is exactly what we want. Let's see. And then we have to come down here and change our test here to say, okay, our list is going to be a link, and it's going to be a box new node, and it's going to, box new node element, and our element's going to be 1024, some number of some sort, and next, and then it's going to be list empty. So hopefully you see the difference between this and the previous thing that we had here. We've basically flipped it around now, where we're kind of always allocating, we're allocating first, and then if the next element is empty, then we don't have to allocate. Whereas before it was the other way around. We were not allocating at first, but if the last element was empty, then we would still have to allocate. There's a question here. Can you prove that final bullet about the allocation concern being resolved? Do you mean this one? I'm not exactly sure what you mean. If you can let me know what you mean, then I'll be happy to talk about it. All right. Great. So we have a list here, and in fact, I think if you keep on reading here, then yeah, this is a good point to add here. We're kind of exposing out the inner workings of how we are. We had two ways of building up our linked list, and we've switched between the two of them. And of course, if we were exposing that to the user would be well aware of how we're actually building up our linked list. Instead of us providing kind of a nice wrapper API around it, so that the user doesn't have to look at the inner workings of our linked list implementation here. And so instead, you can do something which is quite common in Rust, where you basically provide a wrapper struct around these inner workings. So now we have our linked list struct here, and the linked list is going to have just a single field head where it takes a list here, right? And in fact, we probably want to call like this link and something like non-empty. All right. We can do link, non-empty, and link. All right. And this will become important that we're providing this wrapper here in just a second. Now, there's one particular aspect that kind of calls out to me when looking at this, right? This link element here is either empty, so it either doesn't exist, or it does exist and it's a box node. And so we've implemented what essentially in standard Rust ends up being an optional type. And an optional type, if we look at option here, an option type is either none, it doesn't exist, or it's some, it does exist, which is exactly what we have here, just with different names. And so instead of our link being, you know, and our own enum that we implement here, we can just do link as a type alias around option box node, just like this. And this is effectively the exact same thing that we had before, except now we get the standard libraries implementation on top of it, and we'll be able to take advantage of all these nice APIs that standard libraries option comes with. Excuse me, thank you. All right. So now that we've gotten that sneeze out, we can change this here. I think we can go ahead and do link some and link none. And in fact, we don't actually need link : here. We can get rid of those and just do some and none, because those are available for us to use. All right. Let me know if you have any questions here about why we chose to Gesundheit. Oh, thank you. Oh, that's Yiddish, isn't it? Or is it Dutch? I'm always confused. Sometimes when I see Dutch, I think it's Yiddish, and sometimes when I see Yiddish, I think it's Dutch. So, yeah, let me know if you have any questions about this here. But we're basically, you know, re-implementing what we had before using the standard option type instead. This down here, where we're actually creating our linked list, is you know, we're actually not creating this linked list struct here, right? So we'd have to do something like linked list head and hopefully, yeah, there we go. So now we have an actual linked list here, but this is really nasty, right? It would be nice if we didn't have to write things like this. And in fact, if we're creating a library here, and users of this library won't even be able to write code like this, because head here is not public. In fact, nothing in our library is public yet, so we should probably do that right here. And now things are good. Like linked list is the only public thing, so our public API for this library is just this linked list type, and users of our library don't even have access to these things here. They won't even be able to construct this. Which means, right, that we have a linked list that users of our library can do nothing with. They can refer to the name linked list, but they can't create the linked list, because the only way to create the linked list is to build up a node, and they don't have access to node because node is private, right? So we need to provide a way to actually expose this out to them. And that we do that by building up some nice, you know, methods for them. So our first thing we're going to do is a constructor function of some type, which by convention is called new. Linked list here. And we're going to do linked list with head being equal to none. So this is the empty linked list here. We could also call this empty if we wanted to, like this. So now we have a way of actually constructing a linked list by saying linked list empty. All right. Hopefully this makes sense to everybody, that we have a way of constructing an empty linked list here, where we've simply specified that the head of our linked list does not exist. It's none, right? All right, great. But now we need to have, this is where things get really fun. Now we need to have a way of actually pushing an element onto our list. So let's go ahead and create a push function here, which is going to take a mutable reference to self, because we want to mutate self here, and it's going to take the element, which we've hard coded to be a U32 here, and it won't return anything. And we can just use the to-do macro here so that it will compile. And in fact, like implement to-do. If you've not implement push, if you've not used the to-do macro before, this is simply a way of saying let the code compile, but if we run this code, it will crash right here. Chad is asking, are we going to be using iterators in this implementation of it? Yeah, we can go ahead and implement an iterator, assuming we'll have enough time. All right. So down in our test, then the best thing to do is list.push and 1024. And of course, we have to mark our list as mute because we're mutating it. Oops. And this compiles, but if we go ahead and do cargo run, cargo test, it crashes saying not yet implemented because we have not implemented this push method. So let's go ahead and do that. So we have to ask ourselves, like, what do we actually want to do here? Well, the way that a linked list works, right, is you take the head of the linked list and you construct like a new node, and you make the former head of the linked list the next link in that node, right? I'm wondering if in here we have some nice visualizations of a linked list, just to thought we did. Yeah, here. This is not exactly how this is not the best. Anyway, let's just think about this again logically. You have the head of your list, and it points off to more things, and it has an element in it. You want the new head of your list to basically be another node that is pointing to the previous head of your list, right? So let's start writing this in a somewhat naive way, right? We can match on our head here and see, like, if we don't have a head, then our head is simply going to be equal to box new, it's going to be sum box new, and then we just do link with the element and the next is simply none, just like this. Oh, and sorry, this is node. So this is the easy case, right? We didn't have any head before. Our head was empty. We have an empty list, right? And now we're just setting the head of our list to be a boxed node where the data inside of that is what was passed into us for push, and the next element is none. So now we have a one element linked list, right? And if we do sum to do, then this is working fine. This completely compiles fine. We are not implementing the sum case yet, so this is fine. This compiles fine, and in fact, if we run it, the tests pass, right? We don't crash or anything like that. But of course, now if we go ahead and push another element onto it, 42 here, then it will crash because we've reached this point where we had a head of the list, and now we need to actually go ahead and implement this as well. So hopefully that makes sense to everybody. Let me know if it doesn't, so we can go over it again. So now we need to make the decision, and you might be thinking, okay, so this is the node that was the previous head of the list. What we want to do then is to construct a node, a new node, where the element is whatever was passed into push, and the next element is the previous head of our list, like this. Okay, of course, we're not quite done yet. This is our new head, right? And then we say self head is equal to new head. And this is where we run into issues, right? Oh, and of course, right now we're running into the issue that we have to wrap this in a sum. And this is where we run into issues. And the issue is right here. We are moving out of self.head right here, which is behind a mutable reference. Let's compile this here, and this becomes a little bit more transparent what's happening here. So we're matching on self.head, and when we match on self.head, then we are moving out of it. We're trying to like rip out self.head from self. We're trying to like take the head from it, rip it out of the thing, and we can't do that. We can't rip out pieces of our data structure because we don't own that data structure. The only time you can move things out of a data structure is when you own it. Otherwise, you're simply borrowing it. And just think about it. If you were to try and rip out the head of this list, what would be left, right? There's nothing there, right? Nothing would be left, and that can't be, right? We need to leave something in its place, right? Chad is asking, is there any comparison between Rust compiler and C++ compiler code optimization to similar output? There's a lot of comparisons between the two. It would be, I think that's a very, very, very broad question, like comparison. I think you'd have to have more specific questions for us to like dive into that. And Chad is also asking if we're going to get into doubly linked lists today. Unfortunately, I don't think we'll have time. I'm trying to take this slow, and I don't think we'll have time to get the doubly linked list. But we can go ahead and do that maybe next time. And you should be able to do doubly linked lists without unsafe. That's certainly possible, although it probably is not the most performant doubly linked lists if you don't use unsafe. Cool, and there's a little bit of a spoiler alert inside of chat, which we'll get to in just a minute. All right, so we have the head of our list. What we want to do with our head of a list is basically take the head of the list, like put something in its place and say like, okay, the head of the linked list temporarily is here. Stash the old linked head of the list inside of our new head, and then set the new head of the linked list. And in fact, there's a good reason why we can't do this way. In particular, like when we rip out the old head of the list here, we don't have anything kind of sitting in memory. We can that is valid sitting as the old head of the list, which is fine. Like inside of this function right here, because we're like the next line we're setting that head to be the new head here. But just imagine, for instance, that we panic right here for some reason. If we panic right here, then other code will be able to see that we've ripped out the head of the old list, and then that can lead to a whole bunch of terrible things happening here. So Rust is preventing us here from ever being in a memory invalid state here, where the head of the list is just kind of invalid memory essentially. All right, so how do we actually handle this? Well, we need a way for taking the head of the list and replacing it with something else and giving us access to the previous head of the list, right? Looks like we have a spammer inside of chat, which is unfortunate. hold on 1 second here. Just going to take care of this real quick. Oh, it seems like I can't. Seems like I can't take. Hopefully that doesn't get any worse, but we'll keep our eyes on that. All right. So we need to replace the head of the list at this point with kind of a placeholder, right? And there's a perfect standard library function for doing this, and that is standard mem replace. And what standard mem replace does is it takes a mutable reference to something and an owned value and places the owned value at where the mutable reference is pointing to and returns back the old value. So let's write some code so we can see what that actually looks like. What we want to do here, I'm gonna comment this code out here. We want to replace our head of the list with nothing, with none. So temporarily the head of our list will be empty. But what standard mem replace gives us back is the old head here. So now self.head is none, but old head, this value that's on the stack, is the old head of the list. And then when we have that, we can simply build up one of our nodes where we say box new node element is whatever was passed in, and the next is our old head here. And this is our new head. And now we can set self.head to the new head. And this should compile just fine and hopefully run just fine. And it seems like it is. So let's take a step back and figure out exactly what's going on here again. Take it very slow here. We have essentially replaced the head of our list with a temporary holding value of none. So our linked list is temporarily empty, giving us access, full-on owned access to the old head of the list. Then we build up the new head by creating a node and setting the next field to the old head. And then we set self.head to equal that new head. And this means that every point, head is pointing to a valid value. Now you might be thinking to yourself, okay, well, between this call here to stdmem replace here and this call here to setting the new head, self.head is equal to none, which isn't true, right? Like, we are kind of temporarily erasing the fact that our linked list is potentially non-empty and lying and saying, oh, temporarily it's empty while we kind of build up the full tree. But that's totally fine. That is the only way that people will ever be able to see that potentially is potentially during a panic unwind when, and this is getting way ahead of ourselves. So we don't really have to worry about this. And in fact, like, we don't even have to worry about thread safety or anything like that here, because we have an ampersand mute self here, which means we have exclusive access to self. So there's no other thread possible that's pointing, to the linked list here and being able to observe that we're temporarily setting the head of the list to none. We have exclusive access to our linked list here. So chat, let me know if that makes sense. And of course we had if you were following along in chat, we had a little bit of of a spoiler alert, and sorry to call it a spoiler alert. It's not it's not a big deal. It's really great to see people in the chat offering up answers to how we could solve this. This whole idea of an optional value, where we want to get the inner value of an option and replace that value with none, just like we're doing here. This pattern here is very common. It's so common, in fact, that option comes with a shortcut where we can say self.head.take, which does exactly what we had before. Let's take a look at the documentation for take. Take says it takes the value out of the option, leaving none in its place. So if the value is set, then we get the value. You know, if x here is sum2 and we call x.take, then y here is equal to sum2, and x has been replaced with none, which is exactly what we want to do. We want to replace head with none and get back the old head here. All right. So now we have push. Any questions about this? Hopefully this makes a lot of sense. Hello, Hypermanu, how's it going? This is essentially a fully working linked list, except of course that we're missing a bunch of important functionality here, but at least we can construct our linked list fully. Will the video be available somewhere? Yes, I'm recording this and will be available on YouTube later on. And of course, if you're watching from YouTube in the future, hello. So and chat is asking a very important question here. What's the difference between none and the invalid memory configuration? Both are invalid states on panic, right? They are both invalid states, but one is a much more serious invalid state. And this is kind of the reason that Rust exists. The invalid state where the head of the list is temporarily set to none is potentially a little bit of a business logic error, where our list has been made empty, which is totally fine. Like push, like we have ampersand but self here. Like we make no promises. Like we're allowed to make the list empty here. Of course, push, making the list empty on push is not kind of correct from the standpoint of doing what push should do, but we're allowed to do it. Having the head be invalid memory opens yourself up to a whole bunch of potential nasty bugs that can be quite dangerous in terms of security and stuff like that. And so at the end of the day, you have to remember Rust is a memory safe language. So we want to have a language where we always have a fully memory safe view of the world, where all of the memory that we're accessing is always valid. Because if we don't have that, then you open yourself up to very interesting and very hard to track down bugs. So there's kind of a key difference between kind of business logic invalid states versus invalid memory corruptions, essentially, is the way that you can think of it about it. It's not a invalid state, it's a corruption of memory that we are avoiding. Hopefully that makes a little bit of difference. Yeah, chat is saying, for the example, the invalid memory could look like a valid node, but the pointer to the next code could point to arbitrary memory. Yeah, which is a great way of saying, like, sometimes you have a bug and you don't even know you have a bug, right? If we set it to none, then the code that is able to view that, let's say in a panic handler somewhere or something like that, potentially, you know, they can look at it and say, oh, this list is just empty or whatever. That's fine. And in fact, the code, it's not leaking memory or anything like that. Like the elements in that list have been freed as well, so it's totally fine. But if you were able to expose invalid memory, then it's potentially that code could look at that and say, oh, this is a totally legitimate list, and chase down memory and go into memory that is not correctly allocated, and then really weird things can happen from there on. There's a thing, I think in this case, if we don't take the head, we can double free the memory. How so? So no, we can't double free the memory because, and this is great. This is a perfect example. Like there's a question about, can we double free the memory here? And the answer is we cannot. And you know how I know? Because we've only written safe Rust, and in Rust you cannot double free memory. It's impossible. So we have definitely not double freed memory, but let me know what makes you think that we might have double freed memory, and we can talk through what's actually happening there. But this is a really great point about how if in another language you might have to worry, are we potentially going to double free memory? Or even in unsafe Rust, you have to worry about double freeing memory. But in this particular case, we don't have to worry about it because we know we're writing safe Rust, and in safe Rust, you cannot double free memory. All right. Let's really quickly go through and see if we can write a pop operation, which is essentially the opposite of push here. This needs to be self. And when we write pop, we want to return back an option U32 here. So if the list is non-empty, we'll return a U32, and if it is empty, then we will return none. Yeah, so so Chad is wondering about the double freeing of memory in here inside of push. If we end up copying, old head here, right? Well, here's the great thing: we can't copy this old head in the sense that we can't create an aliased pointer to the old head like this. We can't create a box that also points to the same node. We can clone it, where we would essentially just create a deep copy, what is known as a deep copy of it. But box node in Rust does not allow you to make a shallow copy, does not allow you to alias the pointer that's pointing to the node here. For this exact reason, box node in Rust, or box T in Rust, is an owned pointer. It's an exclusive. You can think of it in C++ like unique pointer. It is an exclusive pointer to the thing that it owns. And so there's no possibility for you to copy the pointer there. You can only do a deep copy, which would essentially just reallocate all of that memory, and you'd have a completely deep copy of the thing. And this is exactly what we're talking about with Rust, where you can't run into these issues. And the reason for that is because in safe Rust, these issues just do not exist. They're impossible to introduce. And in fact, you can use this as a challenge. Think of all the interesting things that you've run into in Rust with double free, use after free, and stuff like that, and try and write safe Rust where those issues occur, and you won't be able to do it. Now, you can write unsafe Rust where they do occur, but that's for another video where it's a little bit more advanced. All right. Hopefully that answered your question, and I don't mean to antagonize or anything like that. This is a really great learning opportunity for understanding the safety properties of Rust. These issues just cannot occur. Cool. So let's do pop real quick. And pop, like I said, does the opposite of push, where it kind of takes the head of the list and removes it, right? And Chad is saying, make illegal states unrepresentable. That's essentially what Rust is doing. It's making these types of states impossible to introduce. Yeah, and Chad is clarifying maybe the point of what Chad was saying. Like, Yes, I see here. Exactly. Like exactly as you've said, if Rust were allowed to allow you to copy the pointer itself, then it would end up double freeing the memory. But Rust doesn't allow you to do that, and that's why it's fine to do this in Rust. But in C, it's not fine. In C, you have to worry about this stuff. Awesome stuff, chat. Thanks a lot for that. It's great. So for pop, we're really gonna do the exact same thing. Like we're gonna get the old head here. This is the old head here. We can match on old head and say, you know, if it's some thing in there, then we can go ahead and get the node out. And the node, we can go ahead and get the element from it and return the element like this. And if it's none, we'll return none here. Oops, and I gotta put the and this is almost what we want, right? But now we've essentially made the entire list empty, which we don't want to do. And really what we want to do is say self.head equals, I'm trying to think what the best way to do this here is, because what we want is in here for self.head to equal, this is probably the best way. Next. And this is fine. So we're essentially taking the head of the list, replacing it with none. Then if we had an actual head of the list, we set the head to be whatever that head was pointing to before. And so now what it was pointing to before is the new head of the list, and we return back the element. And otherwise, if we didn't have an old head of the list, then we can't return an element, so we just return none. And in fact, this is a very common pattern here where you're matching on a value, and if it's some, you do something, and if it's none, you just return none here, and that is a map operation, so you can do this instead. And this is the same exact thing here as before. Oh, and of course, all right. So this is pop done right here. Let me know if you have any questions about pop. And I think the last one that we need to do is peek. And what peek does is let us look at the element where we're returning back a reference to the element instead of returning back an owned version of the element. So we're not kind of like taking away the element at the head of the list. We're simply like providing a reference or a pointer to it. And chat is asking, you don't need the old head variable anymore. No, in fact you don't. We can just do this instead. Oh, and yes, I've misspelled peak to be like the peak of a mountain instead of peeking at something. I don't think you need the temporary variable. I think that the bar checker is able to, oops. Yeah, the bar checker. This code right here, I believe, used to not compile in Rust 2015 because the bar checker wasn't capable of understanding that self.head here is not mutably borrowed anymore. But now it does compile. If that doesn't make any sense to you, then don't worry about it. All right, and then peak is pretty simple in that, and of course, peak needs to return an option because the list might be empty. And if the list is empty, then we can't return back a value here. And we can look at self.head here. And if it's sum, then we return back in.element. And I'm always forgetting this right here. And if it's none, we return none. And this is not compiling here because of this. This is not compiling here because we are trying to move head out of when by default, when you do self dot something, you're trying to move it, trying to rip it out of the thing that contains it here. And we don't, we simply want to borrow head. We want to take we want to look at it, but not take ownership over it. So we can do this instead. And this is the same reason we need ampersand here as well. If we try and do this, it will complain. It will complain in this case because the types don't line up, but we need that as well there to borrow n.element instead of ripping n.element out of the node. And again, we can just do self.head.map in.element. And this is exactly the same thing that we were doing before. Oops. And this doesn't compile for the same reason. We're still trying to rip out head from self. We're trying to take ownership of it instead of simply borrowing it. And the best way to borrow an element inside of an option is by using this asRef method here. And we need this as well. So that is equivalent to what we previously wrote. And, you know, depends on taste which one you think is more readable. I think in this case, I might actually prefer the match statement, or the match expression instead of this this style here. All right, we're reaching the end here. And the last thing I want to do real quick is simply just make this generic, because we're hard coding this element here, this U32 element here. Wouldn't it be great if we could keep anything inside of our linked list here? And so if we go here, let's make this a generic type T. And it's a generic type T. It says, I don't know a type T. By default, it doesn't know that this is generic, right? It doesn't know that it's looking for a generic type T. We need to say that node is generic over some type T. And now it's fine. And we basically need to allow this to kind of bubble up and say link itself is also generic over some type T, so that we can pass that into node. Of course, now link is generic over type T, and link is generic over some type T, and that means linked list is generic over some type T, and that means here that we need to be generic over some type T. If we do this right here, again, impl linked list T is looking for an implementation for linked list where the element of the linked list is some concrete type called T, which there is no concrete type called T, right? And in fact, a lot of people don't know this, but you can have different implementations of things for different concrete types. So we can have some methods that only work on linked list when the element is a U32, and we can have another implementation that only works on linked lists of strings. And these implementations here will be methods on linked lists when the element is a string and no other time, right? And so in order for it to say this is this is the implementation for a linked list for some generic type t, we have to first say we have a generic type called t. And now this knows that this t is the generic type t that we've previously defined. And we're getting an error here, right? Because we're passing in a U32 and it expects a type t. So we have to change this to t. And we got to change this to t. And we got to change this to t. Yeah, and peak is rightfully saying that chat is rightfully saying that peak doesn't need to take a mutable reference, because we're not actually mutating the linked list when we peek at it. We're just looking at it. So thanks for pointing that out, chat. And this is it. We basically have an implementation of a singly linked list in Rust. You know, it's not that bad, right? The reason that this is oftentimes talked about as, you know, being not the easiest thing to do when you're first learning Rust is because you do have to have a little bit of an understanding of how ownership works, right? If you go through the naive way of doing things that we saw before, where we were simply trying to rip out the head of the list and not replacing with anything, Rust prevents you from doing that, because that would leave memory in a bad state, and in Rust you cannot do that. And so we have to go through a little bit of extra mechanics here, which are not boilerplate, right? This is, you know, we do that in one little method call here. So it's really not that difficult. But you know, we do have to go through a little extra work here to always keep our linked list's memory in a good state here. And chat is also saying we could also implement our own drop implementation so that it doesn't recurse through the entire data structure to drop it. We could. I'll leave that as an exercise to the reader. There are definitely a few things that we could do to optimize this a bit further. But I mean, this is a linked list, generally how you would write it in C, except for the drop impl that we're talking about, where you would probably loop manually and free things. But it's nice to know in Rust that we get we don't have to write a drop impl here. Our memory will be freed when our linked list is dropped for us, because the linked list will drop its link. When the link gets dropped, it drops its box. When the box gets dropped, it drops its node. When the node gets dropped, it drops its element and its next link, and so on recursively all the way through until there's nothing left to drop. So we don't have to worry about drops, even though there's potentially a slightly more performant way of doing drops than you get out of the box for free. And one last thing the chat is mentioning, using uppercase self here. We can, for instance, if we don't want to refer to linked list here because we might change its name in the future, we can call it self. This is the self type. It just refers to the type of the implementation. You often see this. I don't believe you can do this here for generic types. You can't write self like this. That doesn't work, unfortunately. Type arguments are not allowed for self types here, so we don't get that for free. But this is one potential cleanup that we can do here. Oh, and just self works. Okay. So we can do this. Great. So now we're not explicitly naming linked lists here, which can be useful if you don't want to have to repeatedly say linked list all the time. All right. So the last thing that I'll mention while we wrap it up for today is this was a singly linked list, right? There are doubly linked lists where For our singly linked list, right, the node simply refers to its next node. And a doubly linked list, a node refers to the next node in the list and the previous node. And this is somewhat difficult in Rust to do. I should say it's a little bit more difficult to do it in a safe way in Rust, but it's not that performant, and it's pretty darn difficult to do it in a very performant way in Rust. Again, the standard library comes with the doubly linked list implementation. If you really need a doubly linked list, just use the standard libraries version. But most of the time, you don't need a doubly linked list in Rust. Just use VecDeque. That's like 99.9% of the time what you need. So we will. It seems like there's enough interest, and perhaps I'll come back next week with a stream on doubly linked lists instead. And of course, VecDeque is a great an even better potentially way of replacing a doubly linked list, because VecDeque is just like vector, except that it allows you to pop from the front of the vector and the back of the vector, instead of, for vectors, it's just the front. All right. So just finishing up with a few questions here. Yeah, the docs on standard collections for linked list. I think we looked at that before. Start with, it is almost always better to use Vec or VecDeque because array-based containers are generally faster, more memory efficient, and make better use of CPU cache. And they're also, yeah, just use Vec or VecDeque. Unless you really know that you need a linked list, use Vec or VecDeque. And the chat is also mentioning also with slabs, you can do safely and even faster than usual. It's basically just use the Vec. Yeah, so slabs are a way of basically like chunk allocating memory, just like you would do in a vector, and then using indices to build up a logical linked list, but where all of the elements are allocated in one continuous array of memory, instead of how we're doing a linked list here, where each element is boxed. It can be anywhere in memory. The allocator is free to put it where it is. With a slab, you basically create, in a way, your own allocator, which sounds more difficult than it actually is. But that's also an interesting thing that potentially you can take a look at, is creating a linked list using a slab instead. All right, any more questions? If not, then I think that we're going to end the stream for today. My goal with this was to take things slow. If I didn't take it slow enough, if you're still lost, feel free to reach out to me. And you can see up here, up top, at the very top of the screen, you can see my my Twitter handle, my GitHub handle, where you can search for me on YouTube as well, where I'll put the video for this after the fact. So let me know if you have any questions. If you followed the stream today, then you are very much on your way to being a intermediate Rustation, very much on your way to understanding the borrow checker and how memory management in Rust works. So this is definitely not something that you should just take for granted, and this is kind of the foundation of Rust. This is something you should really spend some time learning if you want to get into the language. So make sure to give this another view on YouTube. And thank you, everybody. Thanks, chat, for a great discussion. And it was a real pleasure, and hopefully I will see you next week. Maybe we'll do round 2 of this, where we just try to tackle a doubly linked list, which will be even more fun. All right. Appreciate everybody, and have a good weekend.